Hello there, in this video I'll talk about the inventions of Eratosthenes. His three major discoveries include being the first person to approximate the Earth's circumference by using the location of two Egyptian cities, a century before the Greek astronomer Poseidonus of Rhodes used to start Canopus as a frame of reference for more accuracy. This method leads to the modern parallax method, which determines the distance between stars with the assistance of luminosity instead. He also invented the sieve of Eratosthenes, which is an intuitive algorithm that determines the quickest way to find all prime numbers in a set number between any interval. This method of finding prime numbers is still used today. His armillary sphere is less well known because it does not follow Copernicus's heliocentric theory, meaning for Eratosthenes everything revolved around Earth. At the center of the model is the Earth, while each successive ring shows the name of constellations or other planetary objects. So this is a quote by Eratosthenes. He said this: Eratosthenes declares that it is no longer necessary to inquire as to the cause of the overflow of the Nile, since we know definitely that men have come to the source of the Nile and observed the rains there. So Eratosthenes, or Eratosthenes of Cyrene, was born 276 BC in Cyrene, Libya. After studying Alexandria and Athens, Eratosthenes settled in Alexandria, Egypt, about 255 BCE. And became director of the Great Library there. He died there in 194 BC at the age of 82. Why? Because he was afflicted by blindness in his old age and committed suicide by voluntary starvation. As a Greek scientific writer, astronomer, and poet who made the first measurement of the size of the Earth, many of his details are still unknown. His only surviving work is a book called Katasterisms, a book about the constellations which gives a description and story for each constellation, as well as count of the number of stars contained in it. However, this book contains information that has already been mentioned before, doubting its credibility. His mathematical work is known principally from the writings of Greek geometer Pappus of Alexandria, and his geographical work from the first two books of geography of the Greek geographer Strabo. So here I have a map of modern-day Egypt. Eratosthenes measured the circumference of the Earth by using simple tools. He knew that at local noon on the summer solstice, June 21st, the sun was directly overhead in the southern Egyptian city of Syene, casting no shadow on a vertical wall. However, in Alexandria, which is located north of Syene, the sun was not directly overhead at the same time and cast a shadow on vertical objects. Eratosthenes reasoned that the difference in angle between a vertical at Alexandria and the vertical at Syene would be the same as the angle between the two cities and the center of Earth. To measure this angle, Eratosthenes placed a vertical rod in Alexandria and measured the length of its shadow at local noon on the summer solstice. He found that the angle between the equivalent of 7.2 degrees. This diagram shows the rays of the sun hit at different angles, but keep in mind the distance from the sun to the Earth is so far that it's basically parallel, which is also deduced by Eratosthenes. He then used this angle along with the distance between Alexandria and Syene, which he had obtained from travelers, to calculate the circumference of Earth. The actual distance between Alexandria and Syene was about 800 kilometers. Knowing this distance and an angle of 7.2 degrees, Eratosthenes calculated that the Earth's circumference was approximately 40,000 kilometers. This was a remarkably accurate estimate, as the actual circumference of the Earth is about 40,075 kilometers at the equator, with only a 0.2% error, at best. See, the unit Eratosthenes used was stadia, which is 600 to 625 modern feet, which itself is a 4% error, which means his measurement of Earth's circumference may have varied by 0.5 to 17% from the value accepted by modern astronomers, but it's in the right ballpark. For those of you who still don't get it, let me make two analogies using math and modern-day science. First, circular motion. Consider the axis from the center of Alexandria to center of Sun to the axis of rotation named point S and point A. Since the city of Syene is southeast of Alexandria, we'll call that point S. For S to exert the same torque such that the net torque is the same magnitude, the ray must shift backward, making a difference in length despite the same rays hitting, creating a long shadow and constituting the same logic for ratios between triangles. This logic continues to the parallax method, which determines the distance between two stars, given the angle of two stars in arcseconds from an observer on Earth. In other words, the reflective method of Eratosthenes. Given the length between Earth and two stars, which can be determined using the luminosity of the equation, the distance between the two stars can be determined using the law of cosine, which could in turn to be used to confirm Eratosthenes' approximation. So the sieve of Eratosthenes is a procedure for finding prime numbers of natural numbers in numerical order. After striking out the number 1, simply strike out every second number following the number 2, and every third number following number 3. This is another way to phrase for every prime number, cross out all its multiples, and the rest of the numbers will become prime. Over here I have a list of numbers from 1 to 100. So let's follow the steps. Cross out 1. 2 is a prime number, so we're going to cross out every multiple of 2, which is every other column. We didn't cross out 3, which means it's prime, but we have to cross out every multiple of 3. We didn't cross out 5, that means 5 is also prime. So we cross out all the multiples of 5. It's already crossed out here. Then we get to 6. 6 has been crossed out, which means it is not prime because it's a multiple of a smaller number. 7 we didn't cross out, which means it's prime. And then this logic should carry out through the whole chart, and we can prove this method works by using Python. So you have num equals int of whatever you wanted to say. So if you have just say numbers all the way from 2 to that number, and there should be 2 lists, one for prime numbers and one for composite numbers. So if we know the number if the number we're at is not composite because we did not see it as a multiple, that means we have to add to the composite list all the multiples for this number. And you would do that using, I spelled composite wrong. So the double slash means the integer quotient. And you would add all the multiples in the interval. Since the number divided by k is the number of multiples such that k times I is smaller or equal to the number. Okay, and then we're going to add it to a prime number because from line 7 we know it's not composite. Let's print this number, and when we're done, we print the primes. That should be it. So let's test using a number, smaller one, 40. All of these are prime numbers. I don't think we skipped any, but since this is a brute force method, if we use 1,000, it's gonna take a lot more time. If you use 100,000, yeah, the numbers are getting way slower because you're using this method to count the numbers of multiples ahead. And that's all that is to it. Thank you. Our armillary sphere was often credited to Chinese astronomers Shishen and Ganda in the 4th century BCE, but Eratosthenes developed it about 100 years earlier in approximately 225 BC. So the armillary sphere is a type of astronomical instrument used to model and understand the movements of celestial objects, such as the sun, moon, and planets. Eratosthenes is credited with inventing the armillary sphere, which he used to make important observations and calculations in the field of astronomy. The armillary sphere consists of a set of graduated rings, or hoops, that represent various celestial circles, such as the equator, ecliptic, and meridians. The equator splits the globe in half, which is this ring. The ecliptic is the path that the sun appears to follow across the sky over the course of a year. It should be one of these 3 rings, as seen from Earth. These rings are mounted on the central axis represented by the celestial poles and can be rotated to simulate the apparent motion of the sun and other celestial objects. He used the armillary sphere to make important observations to measure the Earth's tilt and the movement of the sun across the sky. He also used it to determine the position of the equator and the location of different stars in the night sky. One of his most famous observations was the measurement of 23.5 degrees, which is Earth's tilt. That also determines the ellipticity of Earth. These observations helped him develop a more accurate model of the solar system, which he could use to make prediction about the movement of celestial objects. However, most of the armillary spheres are, like the one depicted here, they don't usually show the other planetary objects. They might consist of constellations or the moon and the sun, but very rarely do they have the whole solar system. Over here I have a CAD file of an armillary sphere. This is obviously not to scale, or probably what the original model looked like, but as I said before, the only work he has left are in his books, and his models have basically been destroyed, and this is what I think it's supposed to look like. So let me zoom in a little. So from the top you can see this ring, that should be relating to constellations, and you can see that on the words here. And then over here, that is the ring for equator to measure the Earth's location at a particular time for the sun. And then these three rings show the eclipsity and meridian for the Earth, and how they orbit with respect to the moon and the sun. Obviously, the sun and the moon aren't to scale. Their distance from the Earth isn't to scale either, but this is what it's supposed to look like. And then usually it's supposed to be bigger. This one should be able to sit on the tabletop given this base. The one he built was a lot taller than this, and you need, I think, more than one person to operate it because it's a bunch of heavy metals. But this is a basic model of the armillary sphere. And that's all that is to it. Thank you.